Let me introduce our next speaker, Kyle Lowe. He is a lead research scientist at AI2, Allen Institute for AI. He is also one of the co-leads of the Olmo project on open language modeling. And I have to say, he is also one of our Cosmic AI collaborators in the Explorable group. And so working with him has been fantastic. Take it away, Kyle.
Thanks for the invitation. I'll try to keep on time as well. Today, I'm going to be talking about Olmo 3, latest class of models that we released, what's special about it, what it took to get there. For those of you who aren't familiar, the Olmo project is this project where the idea is that we don't just want to interact with models through APIs, we want to actually really understand what goes into developing these models, be able to develop models ourselves. And in order to do that, our belief is that we need to be able to release everything associated with developing a model, not just the model weights that you can download and run yourself, but also the code that is used to train it, all the training data that was used, detailed reports about how to develop this. As scientists, we know that these are important ingredients needed for reproducibility. The latest family of models that we released, Olmo 3, we're pretty excited about it. Olmo 3 is the most complex of the models we've developed, as these models have taken exponentially more effort to get to next tier capabilities. What you see here is a diagram of, from left to right, is progressing through different stages of development. So these days, model development is just you push a button and you wait 2 months for a model to come out. There's actually iterative rounds of increasing some amount of training of certain type of data using different algorithms and slowly progressing the capability of the model, which is on the y-axis up. And you can see our model, our latest model, Olmo 3, performs comparably to some of the models that are released by top groups. Gemma is from Google, Gwen is from the Quinn group at Alibaba, where they're currently the best fully open language model out there and comparable to some of the ones that don't share all their data or share detail about their recipes. So what's special about Olmo 3? Yes, I did show one model and its progression as we climb capabilities through going through these stages. But actually, Olmo 3, what we discovered is that depending on the model you want to build, if you want to build a thinking model, Olmo 3 Think, if you want to build an instruction following model where you don't care about reasoning, but you just want it to do things really quickly, just like write this email. Depending on the type of model you want to build, the recipe that you use to develop it actually changes. So there's we're no longer thinking about it as, oh, you have to go through pre-training, mid-training, long context. These are just stages of development. Yes.
So what was the eval specifically that you had on the y-axis in the previous slide?
Oh, these are benchmarks, pretty commonly used benchmark scores. Depending on the capability of the model, if it's a really weak model, we'll use a certain class of benchmarks that are typically known for base evals. Base models, there's like an average of like 40-something metrics that people use. On the right,
depending on the benchmarks, I was just curious.
Oh, yeah.
Okay.
Yeah, the performance scores do change the performance as a function of benchmarks. These are all the ones that are popularly used, plus LM development. And I guess in this case, what we realized is, oh, when you get closer and closer to post-training, which is crafting the behavior of what the model you actually want to interact with, you might start doing something different. You might actually have different data recipes for each stage. You might actually just branch off. In the process of developing a reasoning model, we realized that actually the intermediate state for a reasoning model is a really good starting point for spawning an instruction following model where you don't actually care about reasoning. It's like some interaction there still. So we're calling this concept of, oh, wait, there's a lot of little decisions that you have to make in order, and all of them lead up to building a good model. And so we're kind of referring to this as like the full dynamic flow of how we make these iterative continual development decisions. And this is what we think is really, really critical for teams to get. So if you want to build a really good model. So why do we care about, what is this model flow or like flowing or continuative iterative development? Well, we care about this because it enables diverse AI research, which I won't talk about a ton today. We don't need to know what kind of AI research we're doing, but like an example is if you're sharing the data, then you should be able to do things like audit the data that's used in training these models, enable better traceability, build applications or research tools such as this tracing tool, where we can, in real time, as the model is generating, trace back any generations back into this training data, because we built a giant index of all the training data. So you can enable things like this. Maybe what's interesting, I was changing these slides last night, but to add some of this, what's interesting for this group is we also think that actually opening up access to all of these intermediate artifacts and tools that we use through the course of development is an accelerant for if you want to build AI applications. So I could talk about very lightly about two projects that build heavily on the infrastructure we developed and released for Olmo, for the Olmo project. So it's not Olmo specifically, but just like spawn-off projects that happen as a result of the main Olmo thread. One of them is Open Scholar. This was published in Nature, I think this month. But actually, this is a really, really old paper from 2 years ago. One of the first attempts from our group to say, hey, it looks like we can maybe build models to do scientific research, like literature reviews, literature synthesis. But at the time, everyone was building, let's just prompt GPT. That's the best we could build an index search and then just prompt GPT. And so this was what Echo was just like, can we actually just train a model to do this? Train a model to be able to be aware of the fact that it's going to be used in this RAG type setting and is specialized for scientific literature review. So this is one of the first works in this case. And the diagram here, you don't have to worry about it, but basically the idea is that user types in a query, some scientific query, and the output shouldn't be GPT hallucinated citations and everything. It should be something sensible. And so what a sensible workflow would be, you probably guess it, is you build some data store, has an index, the language model gets to retrieve documents, iteratively give drafts and feedback, keep generating itself until it finally gives an answer with real citations. And this was the idea. There's a demo if you want to actually play with that. And so at the time, we were comparing against, there was not many other players, maybe some proprietary players. You've probably heard of Perplexity AI. We compared against GPT-4, and we found that our system actually works quite well, even compared to GPT-4, especially on citation fidelity. Once you control the behavior of your model. So there's an example of like, if you build this core infrastructure, you can actually spawn off your research assistants, develop only your own model, not just like being prompting held with GPT-4. Years later, this is recent work from us, which is like, okay, now everything's about deep research agents. It's not that actually different from what people were doing before, but now we're willing to wait 15 minutes until something gives us an answer. And it's supposed to do a lot more rounds of iterative stuff. Again, deep research agents, OpenAI has deep research agents, but these are all proprietary systems. And so again, the thought was, can we just build this ourselves? Is it that hard to build this ourselves if you own your own model? So again, what we did was, it's the same usage pattern. User types questions, an open-ended question, research question. You have access to a data store of research literature. You have access to a language model that you control, you can train to specialize for this specific use case. And you wanted to output long-form reports with citations that are faithful, that are real. If I have time, I have some extra slides on how we actually did this, but it's actually fairly in the weeds. But again, like the pattern is to developing these models. I'll talk more about how we get there today. It's not that different. Whether you're trying to build a specialized model or you're trying to build a general purpose models, the fundamental principles of how do you actually iterate on models is the same. This is us sort of how good can we actually get? This is using an 8 billion parameter model. 8 billion parameter models, just download so many of them on Hugging Face on a whole range of scholarly literature research benchmarks, mostly about paper summarization, multi-document summarization, lit review, answering open-ended or closed-ended research questions in multiple disciplines. And this is us comparing against OpenAI's deep research, GPT-5 plus search, Gemini deep research. And our small model is comparable, sometimes better than even the proprietary models like Perplexity AI. So this is all very doable on a reasonable nonprofit budget. And we can keep it actually really cheap instead of just because companies charge a lot of money for these deep research agents. If you own your own system, you could actually answer queries for like $1. We have to say this. We recently got awarded a large NSF grant to continue with working this line of work. So more stuff in this flavor to come from our group. All right, so hopefully back to model flows and having access to all these artifacts and being able to work with all these artifacts. Hopefully you're motivated to say, okay, maybe I do want to understand everything that goes to working with all these model artifacts so that maybe I can own my own model one day and build these specialized applications. So how do I do that? How do I get my group to have ownership over my own iterative development process? These are the things you actually need. I'm not going to talk about all of them, but I'll talk about just a little hints about each one. You kind of need data, of course. If you don't have data that's in your particular domain, you're not going to be able to really do much. You need to have people in your team with modeling skills. Not because you need to develop novel architectures for your specialized domains. For the most part, transformers get you a lot of the way. But because you need people who are really versed at debugging issues. Because issues will come up when you're trying to train your models, and you need people who would understand deeply what these architectures are doing, what training is doing, just to go from like everything is at standstill to working. You need infrastructure. You're going to need compute, and compute but infrastructure isn't just GPUs for your training. You need inference compute, and if you want to do research agents, you're going to need search, and search is really hard to build infrastructure for. And then there's other things that people don't necessarily talk about, like team organization. How do you actually build teams of people, and how do you experiment reliably so that you always know you're making progress? I'll talk a little bit about each. Data. The way we approach this is we always, as principals, solve backwards on the capabilities we want. We're not in the game building general purpose systems that are truly going for solve every possible thing in the world. I think if you want to do that, you have to have trillions of dollars, massive teams doing this. But if you're really focused on what it is you want to do, the scope of what you want to build, then you should be able to enumerate a reasonable amount of capabilities that you want to target. So in the case of Olmo 3, let's say, we were thinking, Olmo 2, what was Olmo 2 really bad at? It couldn't do any reasoning, it couldn't do any coding, it wasn't specialized in any scientific applications, but it can't use tools. So we just enumerated a few of these and said, this is what we're going to focus on, we're not going to focus on other things. That eliminates a giant search space of other things we have to worry about. Once you have the capabilities you care about, you solve backwards for the data that you think you have a strong hypothesis that probably moves this. So in our case, we were thinking, okay, we care about thinking or reasoning. Where is that expressed mostly? It's in code. We'll go get more GitHub code. It's in like complex math problems. Okay, we're going to have to go find large repositories of math problems. Thinking, reasoning, that means that actually we're going to be generating long reasoning chains, meaning or even and conditioning on that for multiple rounds of generation. What that means is we need our model to actually process long context. So the proxy thing that we need is not just data that's relevant to reasoning, but just data that's just long. So the model has something to train on that knows to learn long dependencies, long research articles, novels, even. Tool use, we need to have similar idea and same scientific applications. Oh, we need to throw in a lot more STEM papers. Maybe not even just specifically my discipline. I'm a computer science psych, but STEM papers in general, anything that could possibly be useful in other fields, because there's some similarities. And so this is what we ended up with. This is the training data that we use for Olmo 3, which we called Olmo 3. The numbers match up. But really the thing to pay attention to is we collected 100 million scientific articles, and then we OCR'd everything. And this gave us a ton of data. This is like a giant piece of our training data that's net new. If you want to compare it to all of archive, this is all of archive. It's like a tiny blip compared to what's possible. So there's actually a ton of research literature out there that's available for use, and all of this really helps. Almost here, thanks for Jordy for bringing this up. One of the big lessons we learned is in order to unlock these PDFs, you have to not be afraid to just build the tools that you actually need to get the job done. PDFs are notorious. If you've ever run any GhostScript or OCR tools to try to get PDF into something that's plain text, it's the worst thing imaginable. And so we were thinking, and in the past we thought, oh, do we want to spend 6 months of our life just solving this subproblem, like change the light bulb, I have to fix the whole garage type of thing. Like, is that worth it? And sometimes it kind of is. We started the OCR project specifically to help us get to that row of data, which is not even the majority of the data. It's like 10% of our data. What we thought was valuable, and it was important because of the capabilities we were solving for. If we were solving for different capabilities, we wouldn't have done it. But this was an OCR system where the idea was, okay, let's just throw as much, I just want to build a tool. I'm not going for any scientific novelty. This is a means to an end. And if you know that that's the means to an end, you do everything in your power to just try to get this as good as possible. So what we ended up with was constant optimization of this tool to get it as efficient as possible. And essentially the target was get to a point where we can actually afford to process those PDFs. So what we were aiming for was if we toss all of those PDFs into GPT-4o at the time, it would have cost us like $1 million or more. This was before batch API, but even then, it was an absurd cost. And so this was born out of an idea. It was like, we literally can't use GPT-4. And the first OCR tool was, okay, but use GPT-4 for a little bit. Generate enough data, keep generating data, and try to distill this down into a model that we can actually run at a reasonable cost. And at some point, because it's a narrow scope tool, I don't need all of GPT-4's capabilities. I just need OCR. And at some point, you can get the cost really, really low to the point where like, now I can actually run it. Now I have my data. So it fixes a whole bunch of these problems that were pretty challenging for OCR, even like old scan documents like this, a process going well. And this is how we treated it. We didn't treat it like a research project. We treated it like a tool, a means to an end. We open sourced it and we just kept developing. And so the surprising thing is sometimes if it's a tool that you need, other people need it too. And so you can see the interest in OCR and the benchmark performance of OCR benchmark performance before and after we released this tool. We noticed that GPT-4, it wasn't us also, it was like other people were noticing GPT-4 was really good at PDF extraction, but none of the other models are using it. Gemini is like down here. Some of the other vision language models weren't doing it. And as soon as we released this, Mistral dropped the API, and now everyone is doing the same type of technique. Vision language models are standard now. And there's like, CVPR has a ton of these sessions. And it's because people realize this is actually really useful. And if it's useful, it'll get published, it'll get rewarded in some way. So the incentives align.
But what is the current, maybe you will show, what is the current level where like GPT 5.2 is on this?
Oh, those things are probably amazing. Yeah, but at the end, it's like cost. I think you can probably get to, I think there's probably some, there's a lot of really good groups from China right now. Paddle OCRs, Monkey OCR, they're releasing really good models nowadays. Yeah, I don't know. At any given week, I think like we released our last model in the same week as like 3 other groups, like just like back to back in the same week. So I can't even keep track at this point. Nice thing about us is, unlike these other for-profit incentives, we release all the data. So if you want to train your OCR model, you can literally download all of our data, train it, and retrain a version, make a better version. All right, so that's just getting your data. Once you get your data, you also need to have a good team. You have resources and have infrastructure. For Olmo 3, this is what we had. We had access to 2,000 H100s for about 6 months of development. 2 of those months were burst training on 1024. So this is like when you finish your experimentation, you actually have to carve out this dedicated amount of compute, and you want to train for about 2 months. 2 months includes pre-training, post-training, all of the stages. You don't really want to go beyond that, because imagine your team just sitting and stressing about a model that's training for 6 months. By the time 6 months have gone by, the world has changed. Do you still care about the model that you initially launched? Like, you really want to shorten the enough. That's why burst training is really important. But ongoing development takes quite a while.
Do you own this cluster or rent this cluster?
We rent it for 3 years. Okay. Yeah. I think that's actually very reasonable. GPU improves so fast that by the end of 3 years,
That's right.
you were gonna get, yeah. So order of scale of stuff that you need. You don't need tens of thousands of GPUs. You can do something reasonable. Yeah.
Quick clarification, wasn't the NSF grant to build your own, or was it entirely still software?
It was to build our own. It was infrastructure for NSF grant. I think we're still going to go through some sort of compute provider, because we don't want to manage our own pooling the connections. Like, that's just too much. So probably in the same data set, we're like looking at data centers and getting.
Have you spoken to DAC?
I don't know if I've spoken to DAC. Maybe someone with a higher pay grade than me has spoken to DAC.
We can get you with DAC. Yeah.
Data. We just use public data sources. Being in the open source field means that you're restricted to just using public sources. And so there's a feeling that if you just restrict to public sources, you can't build a very good model. I know, and I think one of the things they've been trying to show is like, actually, you could get a lot of the way. Especially if you're very focused and you specifically focus on your specialized domain, you can absolutely get there. And I know Astro has like a strong open source culture. All the papers are accessible and open accessible. So like, I think you're doing fine here. I think we don't have to be worried about, I don't have some super secret proprietary data that only OpenAI has. So I think things are very tractable. And the team, we don't have hundreds of people working on this. We have 30 people core. 30 of them are students. We're also juggling classes and their own independent research. This is all very feasible, but it's only feasible if you have smooth operations. That's the key. Here's an example of smooth operations. It's hard to distill all of it, but here's just like an example of smooth operations. This is training data for one of our later training stages. So not pre-training, but you notice that pre-training was like a few things, GitHub, Common Crawl, whatever. Eventually your training data looks like this, where every single row is like something different. Some different paper published some data said, we're like, yeah, let's train on that too. Let's train on this, train on this too. Some of them is us curated, some of them it's from other places. This is ridiculous to experiment with and make decisions. Should I use that? Should I use that? What else could I have added or not? This is really, really hard to manage. But this is what we arrived at through this method. We had pretty clear roles on our team between people who are on centralized assessment and people who are on distributed exploration. So for centralized assessment, what we had is we have people, a small number of people who are dedicated to experimental methodology and running what we call integration tests. Integration test was we consume all the best ideas and let's see where we are today. We do a larger run for a short amount of time, pulling in multiple best ideas. If it works, it's now the next baseline that everyone has to beat. And so this way you always grow and climb. If you find any issues, then people can then go back and investigate. But this is a small group of people focused mostly on the core methodology and statistics. The distributed exploration allows you to employ tens, 20 students independently working on their own thing. Each person owns a different slice, such as investigating their own particular data idea, and they don't have to worry about others. But for distributed exploration to work, you have to standardize some amount of methodology. So I think about this from like classical statistics. Think about the value of the t-test or the ANOVA or like like these like classical RCT designs. Those are, yes, if everyone had to develop their own statistical test and method, they'd probably be really, really specialized, but you don't accelerate the field this way. Schemas and standardization really helps because it takes off a lot of mental load. And to go, if I can prove that my idea works using this methodology, and I can follow this system and prove that my idea works beyond some epsilon of like noise, there you go, it works. And you can free up a lot of student exploration to just like work on exactly the thing that they work on, and then they offload that idea back onto the centralized team that does the integration. I know a lot of other groups at language model labs will operate in a similar way. All right, so if this holds, then the thing that's the bottleneck is this centralized group being able to do experimentation and propose a standard of experimentation that everyone on the distributed exploration side can actually rely on and trust, that they're not just wasting their time. So this is the hardest part, experimentation and evaluation of your ideas. This is often what it looked like, evaluation looked like when we were first starting out. You would define a bunch of benchmarks. Natural questions is a question answering benchmark. GSMK is a math problem solving benchmark. Even if I was actually a coding benchmark, don't ask this, it's a terrible name with this data set. And what you would do is you try different data recipes, different interventions, like it's different color, and you would train a model. Identical model, change data, holding everything constant, you just keep training, and as x-axis is training for longer and longer, and you just monitor the evaluation. And what you'd hope to see is some separability between these curves. But according to these curves, I have no idea which data was better or worse. What you want is what we ended up with, which is something like this. These are the same models that we ran, but just using different benchmarks. And we noticed that, oh, wait, these pink and green ones, this configuration is really, really good. Whatever that I was doing there was working. And the idea here is really simple. If you want to have good signal, you have to average across a lot of different things. This is why, even if you're specialized domain, you want to have a diversity of different methods of evaluation that target different aspects of the same core thing. And if you take averages, statistics works, noise just goes down as you average more things. So this is part of it. But the other part of it isn't just, okay, average enough things, and then suddenly your noise is gone. It's also choice of your metric. So for your choice of your metric, again, same rough benchmarks that we were looking at before. X-axis is amount of computation put into a model. So you can think of on the left-hand side, these are really, really small models. These are like sub 1 billion parameter models trained for a tiny amount of data. And the x-axis and as you go to the right, you're talking about the big models that people release that you actually use for inference. We obviously want to use small models because if I can get away with all my experimentation on the small model size, half the model size as before, it's the same as if I doubled the amount of GPUs I have. So each time you use a smaller model, you would love to. The problem here is most small models perform at 0%. 0% accuracy or random chance. This 25% is a four option multiple choice test, so 25% is random chance on the left. These are all performing at 0% accuracy. So most of your experimentation at small scale is random, which means it's unusable for experimentation. But you can take the same benchmarks and just be more clever about how you calculate the metric. So in this case, instead of just scoring for accuracy, we look at the language model's probability that's put on the correct answer. And we take the answer that has higher probability. And once you do, we score based on the score, the language model's native score. And once you do this, you see this smooth pattern of as you add more computation to models, you see how the small model then progresses into the large model's performance scores. And this is really, really nice because then you can have scaling laws, you can forecast your ideas out. But this isn't a change to the benchmark. It's the same benchmark. It's just changed to how we calculate our metrics. Finally, the last thing is benchmarks and numbers are great, but at the end of the day, people have to interact with the model because you can't benchmark everything. And here is an example of why. Someone typed this for one of our old models. Briefly tell me how this thing in Florence was taught. The Duomo is like a historical building. And then they typed it into our new model that we almost released. And it said briefly, and this thing kept going. And we didn't have a benchmark for excessive chattiness. We just hadn't built it yet. And we wouldn't have known this unless someone had played with it. So the kids call this vibe evals. It's just does it feel good? What we do on our team is we have a document that everyone plays with our models, and they just constantly paste examples of where our models are bad. And before we release any model, we take the top 3 models that perform best in the benchmarks, we anonymize them, we deploy them, we have the whole team play with them, and everyone votes which one they think is best. And usually you'll coalesce onto which one is actually best, and that's when we actually release, not necessarily the one that's the max score on the benchmarks. So in summary, the whole talk was thinking about model flow, customization of your model interventions to what you want. Build tools. Don't be afraid to build tools. Usually they get rewarded. If it's a useful tool for you, it's probably useful for a lot of other people. Think about organization, dedicated roles. How do you distribute workload across a lot of people? Rebuilding your evaluation suites so you can get meaningful signal at a small scale. And don't be afraid to play with your models. Just constantly qualitative assessment is really important. That's it. Thanks.